Yellowstone's supervolcano may be driven by tectonic shifts, not a deep mantle plume for decades. The prevailing scientific consensus held that Yellowstone's supervolcano was fueled by a deep-seated mantle plume, a column of superheated rock rising from the boundary between Earth's core and mantle. However, new research published in the journal Science challenges this long-standing view. The study suggests that tectonic forces alone are sufficient to heat and drive the magma system beneath Yellowstone, fundamentally altering our understanding of how the volcano operates. This shift in perspective is not merely academic. It has significant implications for predicting future volcanic activity and understanding the behavior of other major caldera systems worldwide. The end of the mantle plume debate. The origin of Yellowstone's volcanic activity has been a subject of intense debate among geologists. The traditional hypothesis posits that a stationary mantle plume heats the crust as the North American plate moves over it. Opposing researchers argued that internal pressures within the crust and mantle were the primary drivers. The new study, led by Lijun Liu of the Chinese Academy of Sciences, utilizes a sophisticated 3D model to settle part of this dispute. By incorporating data on past tectonic plate movements in Western North America, current mantle structures beneath Yellowstone, and the physical properties of the lithosphere, Earth's rigid outer shell, the researchers demonstrated that no deep mantle plume is required to explain the heating of Yellowstone's magma reservoirs. Instead, the dynamics are controlled by the interaction of tectonic plates and the varying densities of the lithosphere. How tectonics fuel the fire, the mechanism driving Yellowstone's activity, is described by the study as a competition between two opposing geological forces. Crustal stretching. The lithosphere beneath Yellowstone has uneven density, with some sections being heavier than others. This imbalance causes the outer crust to stretch toward the U.S. West Coast, similar to dough being pulled thin. Subduction drag. Simultaneously, the remnants of the Farallon tectonic plate are sinking beneath Central Eastern North America. This process drags the bottom of the crust downward, tilting the volcanic plumbing system. According to Liu, these two forces compete directly, pulling open the lithosphere beneath Yellowstone. This tension creates a pathway that connects the surface with deeper layers, drawing magma upward from the upper mantle. This competition pulls open the lithosphere below Yellowstone and draws the magma upwards, said Liu. Why this matters for prediction, understanding the precise source of heat and magma migration, is critical for forecasting future eruptions. Ninfa Bennington, a volcano seismologist at the Hawaiian Volcano Observatory, noted that previous geophysical studies showed magma originating in the southwest of the complex and migrating northeast under the caldera. The new study provides the mechanical explanation for why magma follows this specific path. Jamie Farrell, chief seismologist at the Yellowstone Volcano Observatory, emphasized the practical consequences of this finding. Over the last 17 million years, Yellowstone's volcanic activity has moved across relatively warm, thin crust. In geological terms, this trend is shifting eastward toward colder, harder, and thicker crust. If the source is a mantle plume versus tectonics, the resulting activity may be different, Farrell explained. Accurate modeling of these tectonic interactions allows scientists to better estimate what types of eruptions or seismic events might occur as the system interacts with different crustal compositions. Global implications. While Yellowstone is the focal point, the methodology developed in this study has broader applications. Liu suggests that similar modeling techniques can be applied to other high-hazard caldera systems, including Toba in Southeast Asia, Taupo in New Zealand, active volcanoes in northeastern China. Bennington agreed, stating that this analysis improves our understanding of how magma migrates into dangerous caldera systems globally. By moving away from the assumption of deep mantle plumes and focusing on local tectonic dynamics, scientists can refine risk assessments for volcanic regions around the world. Conclusion. The new research reframes Yellowstone's supervolcano not as a passive recipient of heat from Earth's core, but as an active system driven by the dynamic stretching and tilting of the crust. This tectonic-centric model offers a clearer pathway for predicting future volcanic behavior, both in Wyoming and in other major volcanic zones globally.